Welcome back. We are going to discuss another problem today related to the use of both work energy formulation as well as our laws of dynamics, rigid body dynamics, to understand the idea of normal reaction in the context of free body motion. Okay. So, let us look at an example here. I have a bar here, it is a weightless bar that is pivoted at some point O, and at the end of the 10 meter long weightless bar there is a little weight. We will consider this a point mass for now, and this mass is about 2000 newtons in weight. Initially it is in a gravitational field, so if nothing was done to it, it would be at rest kind of in a vertical position like this. So, this is my initial condition at A. If I give it an initial angular velocity omega I and do nothing else, we are asked to find the point at which it would come to rest. So, let us say this bar would move up and come to rest at some theta f. Now, if I give it a sufficiently high angular velocity, this is our common observation, that this bar would actually do a full circle, and so it would go all the way up to the top and come back. So, we ask ourselves two questions. One, this bar is a weightless but rigid bar. So, it is able to sustain both a tensile force in it as well as a compressive force in it. So, we ask ourselves the question, if this was a rigid bar, what angular velocity omega I do I need to make it do a full circle? Okay. The second question we can ask ourselves is, if this was not a rigid bar but a weightless string. So, the difference between a rigid bar and a string is that the string cannot sustain compression, it can only sustain tension. So, if this was not a rigid bar but a string, what angular velocity would I need to give to this string plus mass mechanism in order for it to do a full circle? Okay, so, these are the two questions we ask ourselves. I want you to pause the video and think about this, read the problem statement. So, you understand you try to rationalize in your own minds which one of these two angular velocities should be greater, the one with the string or the one with the rigid bar. That is a question to think about. Pause the video, think about it. After you have done, start the video back again, and you will see the mathematics behind these two calculations and the basic differences between these two calculations. Now, I do not want to take up a problem like this without a physical situation that would describe this. So, if you think of this for a moment, let us say anybody that has been to a circus will see this, the circus act where there is a dome and there is a motorcycle rider that starts initially at the bottom, kind of doing rounds at the bottom of the little steel dome kind of a structure, and the pinnacle of the act is where that person does a full circle all the way around. So, in other words, he is able to do a full vertical circle, where at the top of the circle he is practically inverted, but on the motorcycle. So, we ask ourselves the question, what initial velocity or initial angular velocity with respect to the center of the globe should this person in motorcycle have in order for that person to always remain in contact with the globe, even at the top. So, a model of this problem is where you imagine a little string tied between the center of the globe and the point where the motorcycle is touching the globe, and so that string, if you will, can never come under compression. That means, if that string is unable to sustain the weight of the motorcyclist, that motorcyclist is going to detach from the globe. So, this is a nice model for us to understand a use of this problem. Okay, so, let us get back to the problem now. Okay, we have the bar initially in a vertical position. It has been given an initial angular velocity omega I. Okay, so let us now draw a free body diagram of this at any other location. So, this is my O and this is the body, I will call this P. This is theta, theta positive, theta this way is positive. This is our sign convention, which also automatically means omega counterclockwise is positive and alpha angular acceleration counterclockwise is positive. So, let us say this is moving with an angular acceleration alpha, this rigid bar OP with the mass at the end. The only forces acting on this bar are the weight, which in this problem is 2000 newtons, roughly modeled as the weight of the motorcyclist plus the motorcycle. Now, we also have other forces that occur at O, and in a general way I could have an R sub n, which is the tangential reaction, plus an R sub t, R sub n, which is the normal reaction, and R sub t, which is the tangential reaction. So, I do not see any other forces acting on this bar OP with the mass at the end. That should pretty much explain all the, that should be all the forces. The only other thing we want to include is that the linear acceleration of this, of the center of mass of this bar OP, because the bar itself is weightless, the center of mass of this bar OP lies at the P, at the point P, and that equals L times alpha, where L is the length of the bar, which is 10 meters, which in this case is 10 alpha. Okay, so, the linear acceleration and the angular acceleration are related through the kinematic relationship. So, this is something we are used to seeing in the other problems as well. This is basically coming from kinematics. Okay. So, now we are ready to apply the first law, first Euler's law to this free body diagram. So, let us say, or taking all forces up along A positive, sum of all forces is mass times the acceleration in that direction. Now, we have to be a little careful with this. The reason is, if this bar is rotating at some angular velocity omega, then the acceleration of P has two components to it. If you go back to our kinematics, this L times alpha is simply only the tangential acceleration. There is also a normal acceleration which has magnitude L omega squared. Okay, so, the normal acceleration of the point P, because it is tracing an arc, it is not moving on a straight line. So, you would not encounter this if the body was moving on a straight inclined plane. It would only, you would only encounter the normal acceleration of the point when the body is moving in a non-straight path. So, let us take all, sum of all tangential forces is mass times the tangential acceleration. So, what does that give us? Minus, so if this is theta, then this is also theta. So, minus W sin theta plus R sub t equals mass times the tangential acceleration. So, let us put some numbers. So, this is minus 2000 sin theta. So, I want to leave this at some generic angle theta, plus R sub t is 2000 divided by 10. I am going to, like always, take g is 10 meters per second squared times 10 alpha. A sub t is 10 alpha. So, I have my first equation, minus 2000 sin theta plus R sub t equals 2000 alpha. This is what I will end up calling my equation 1. Okay. The second equation I have is that all forces normal or along the bar is also equal to the mass times acceleration of the center of mass. Here at and an are the accelerations of the center of mass. So, this implies, so I have R n acting in that direction minus 2000 cosine theta, because the weight of the particle acts opposite to the chosen sign convention, that equals 2000 divided by 10, this is the mass of the particle, times 10 omega squared. So, alpha and omega are in general functions of theta. So, let me complete this equation. This is what I am going to call my equation 2. The last equation that will complete this calculation comes from the fact that if I take counterclockwise positive, sum of all moments about the center of mass equals I times alpha. Okay. So, if I go back for a moment, this is my center of mass, like we said, that is G, and there is no other weight in the problem, and the center of mass and P happens to be a point particle. We are modeling the motorcyclist plus the rider as a point particle, the motorcycle plus the rider as a point particle, therefore, its moment of inertia about the center of mass itself is 0. Okay, so let us write this. So, the sum of all moments, if you look at the only force that causes a moment is R sub t, R sub t causes a moment. So, R sub t, diagram once more here. So, I have R sub n, I have R sub t, that is my point O, this is the point P, there is a weight W, there is alpha omega. So, Ig, which is the center of the moment of inertia about the center of mass of the particle, and for a point particle Ig is 0, because it has no discernible radius. So, which automatically means that sigma of mg equal to 0. The only force that causes moment about the point P is R sub t. So, what we find is R sub t times L. If you want to be correct, it has to be a negative sign, because RT produces a clockwise moment and we have chosen counterclockwise moments positive. That is because alpha is counterclockwise positive. So, notice how the sign convention propagates all the way to all the equations. This equal to 0, which automatically implies that the tangential reaction at O is 0. Now, if Ig was not 0, that means if let us say instead of P I have a finite cylinder or some body that had a moment of inertia about its own center of mass, RT is not necessarily 0. Alright, so this is my equation number 3. So, using 3 using equation 3 in 1, let us see if we can simplify this. 1 is the fact that minus 2000 sin theta plus RT is 2000 alpha. So, minus 2000 sin theta plus RT is 2000 alpha. which automatically implies, because RT is 0 as per equation 3, it automatically implies alpha equals minus sin theta. Okay, so we found that alpha equal to minus sin theta. So that's kind of that's what we found from the laws of mechanics. So now if I apply work energy concept to this, essentially I omega d theta. So if I know, if I want to write omega in terms of theta, omega is a function of theta, this is an alternate way of stating our work energy relationship. Okay, to bring it into a more familiar form, Ig W d omega from some omega 1 to omega 2 equals Ig alpha d theta from some theta 1 to theta 2. If I am going from some initial state to a final state, then the work done in the angular sense. So this part here, so this I can replace this part with the sum of all moments about G. So this part is essentially the work done in an angular sense. This is my right hand side. The left hand side, if I simplify that, would essentially give me half Ig omega 2 squared minus half Ig omega 1 squared. And you will all recognize that this is the change in the kinetic energy, change in angular kinetic energy. So we essentially what we wrote down in the linear form as work done on the body is equal to the net change in the kinetic energy of the body is also true when you start thinking of this in an angular sense. So we will go back to this form here because it is essentially a differential form of this integral relationship. The differential form is valid at every point in the process. So at going from some angular position theta to another angular position theta plus d theta, a small increment in theta would allow me, this kind of a differential form will allow me to apply work energy relationship over that differential angular process. Okay, so if I do that, Ig omega d theta equals Ig alpha, and Ig can be cancelled out. So essentially this is half of d omega squared d theta equals alpha. So if I go back and see what we had before, alpha is minus sin theta. So d omega squared d theta equals 2 alpha. Omega squared is omega squared from some initial omega I to a final omega f. Okay, so I have now integrated this, is going from some initial theta I to a final theta f minus 2 sin theta d theta. So this is omega f squared minus omega I squared is equal to the integral of sin theta is minus cos theta. Okay, so that gives, this makes this 2 cos theta, and this evaluated in the limits theta I and theta f. So I will write this one final time, omega f squared minus omega I squared is twice cos theta f minus cos theta I. Now, in this particular problem, we are starting out with theta I being 0. So, the body is completely in a vertical position oriented with respect to gravity. So, theta I is 0 and we want to ask ourselves the first question. The first question is, at what angular position would omega f become 0 for a given omega I? Okay, so let us write the question. At what position, at what angular position does omega f become 0? And if I ask that question, I'm going to erase this free body diagram here. What we find is that omega f squared minus some omega I squared equals 2 times cosine of theta f minus 1, because theta I is 0. So, this becomes 1 owing to the fact that theta I is 0. So, given omega I, we want to find what is the omega for a given omega I, what is theta f. So, I can write this as omega I squared equals 2 times 1 minus cosine theta f, or if I rearrange this a little bit, half of omega I squared Okay. So, if omega I is 0, just to kind of look at chalk out some trivial cases, if omega I is 0, the bar is going nowhere. Theta f would also be cosine inverse of 1, which makes theta f also 0. As omega I increases, for very small omega I, theta f would be slightly positive. So, as theta f increases, as omega I increases, theta f increases. So, just to get at, if omega I squared is exactly 2, if omega I squared is exactly 2, which implies omega I is square root 2 radians per second, then omega I squared is 2. So, this becomes 1, 1 minus 1 is 0, cosine inverse of 0 gives me theta f as pi over 2. So, if omega I squared is square root of 2, that gives me theta f is pi over 2. Now, the next case is if omega I squared is such that what is inside this radical is actually minus 1, that is, this part is not 1 but 2. So, if half omega I squared is 2, that means if omega I squared is 4, which implies omega I is 2 radians per second, what do I have? Then theta f, the final position when omega f becomes 0 is pi. So, if I give an angular velocity of 2 radians per second, that means this bar is going to go up to the topmost position pi, theta f equals pi radians. So, all of this, I mean, we are not going are in the units of angular units of radians. So, if this goes up to the top, then theta f is pi. Now, technically this bar started in this downwards vertical position, and if I give this 2 radians per second, this bar would traverse an arc and come to rest at that point. It would come to rest at the top of that point, which means that if I give it an angular velocity slightly greater than this, slightly greater than 2 radians per second, this is going to complete a full circle. Now let us go back and see what it means if omega I squared is slightly greater than 4 radians square, if omega I squared is slightly greater than 4, what we find is that the argument inside this cosine inverse is no longer less or no longer greater than minus 1. It is actually greater than it is minus 1.1 or 1.2. So if omega I squared is greater than 4, this part can never be, you can never find a cosine inverse of the argument there for real theta. That means the bar would never come to rest. There is no such thing as a theta f at which omega f is 0. It would just continue to rotate forever. Okay, so the minimum angular velocity omega I needed to make the bar go a full circle is 2 radians per second. Notice that this does not depend on the mass of the bar. It does not depend on the actual mass of the particle that you are considering. Alright, so the next question we want to ask is, what is the nature of the forces inside this bar? As if I give only 2 radians per second, will this bar ever experience a compressive force? So let us ask ourselves that question and answer it. So I will write the question first. At what theta f does Rn become 0? And if you go back to our equation 2, it says Rn minus 2000 cosine theta equals 2000 omega squared. Omega b meaning the instantaneous omega. So from here, omega squared minus omega I squared equals 2 times cosine theta minus 1. So at any theta this gives me the corresponding omega. This comes from our work energy relationship. If I now substitute this in this equation 2, Rn equals 2000 cosine theta plus 2000 times omega I squared, I am going to move this over to the other side, plus 2 cosine theta minus 2. So this is Rn. Now if you go back to our free body diagram, we had chosen Rn in a tensile sense to be positive. If you notice, we had Rn pointing away from O being positive. So Rn positive implies the bar is under tension. Rn negative implies the bar is now gone under compression. Okay, so let us see at what theta would omega at what theta would Rn become 0 for a given omega I. So omega I is given, at what theta would Rn become 0. So I will set this to 0 and I am able to calculate what theta I is, what theta f is. So if I go ahead simplify this equation, I have 2000 cosine theta plus another 4000 cosine theta. So this gives me 6000 cosine theta minus 4000 plus 2000 omega I squared equal to 0. So I will just divide by 2000. This is 3 cos theta minus 2 plus omega I squared equal to 0. So Rn is 0. If Rnf is 0, that happens at this theta f. So if I rearrange a few of these terms, that gives me cosine theta f equals 2 minus omega I squared divided by 3, or theta f is cosine inverse of 2 minus omega I squared divided by 3. Okay. So if I ask the question, for a given omega I squared, let us say if omega I squared is 2, which is what we found was sufficient to bring the bar to rest at pi over 2 radians per radians, which is 90 degrees. If omega I squared equals 2, then theta f equal to pi over 2. That means when the bar, if I give this bar square root 2 radians per second, when the bar becomes horizontal, Rn is 0 in that bar. So if I give it, if I give it slightly greater angular velocity, it is going to go past that, but Rn would become negative. So if I do not want, for a given omega I now have a way of finding the theta f at which Rn becomes 0. So if I want to turn around and ask the question, at what omega I would theta f remain positive even all the way to theta f equal to pi. So at what omega I does theta f equal to pi? This says that even at the top of the circle, the bar is only under tension. So if I want to find this, theta f is pi, that means 2 minus omega squared over 3 has to equal minus 1, which means omega is square root of 5 radians per second. So I have to give this initial angular velocity to be square root of 5 radians per second for the bar to remain under tension throughout all the way to pi. So let us go back, compare these two numbers. For the bar to come to rest at the top of the circle, so for it to just reach the top of the circle, if I give an initial velocity of 2 radians per second, that is enough. So if I give it an initial angular velocity of 2 radians per second, the bar would get to the top, and if I give it an infinitesimally small greater amount than 2, it would complete the full circle. That is all I need for it to do the full circle. Whereas if I want the bar to remain under tension all the way to the top, 2 radians per second is not enough. I have to give it an angular velocity of square root of 5 radians per second. Square root of 5 is much greater than 2 in the sense of it is greater than 2, and it require at least square root of 5 radians per second for the bar to reach the top and the normal reaction in the bar to be positive. So, if I give an angular initial velocity greater than square root of 5 radians per second, then I am assured that the bar would always remain under tension. Now, if I go back and look at what happens if I only give 2 radians per second, if I only give 2 radians per second, then omega I squared is 4, 2 minus 4 is minus 2. So, at some angle, if this initial velocity is only 2 radians per second, that means there is some angle, some theta f, which is cosine inverse of minus 2 over 3, at which Rn becomes 0. Rn is 0, the bar is continuing to move because if I give it 2 radians per second, the bar would go all the way to the top. So, for this remainder of this angular motion, the bar is under compression. Okay. So, if you are a motorcycle rider, this is not acceptable. Now, let us make sure we completely understand this one last time. If I give it 2 radians per second, I will get to the top, but the bar would have to sustain a compressive force from this angular position to the angular position theta f equal to pi. If I give it square root of 5 radians per second, the bar would get to the top easily because 2 radians per second was enough to get it to the top. The bar would get to the top easily and the normal reaction in the bar would become 0 only at the top. So, if I give it slightly more than square root of 5 radians per second, the bar would complete a full circular motion with the bar being in tension all the time. Okay. We will continue this discussion in another example problem.